Alright, so before we start, thank you so much for coming here today. I'm Nasir, will be your MC, and we're at Arvato Systems for a nice office upstairs and here as well. Okay, so shout out to Arvato for giving us this space. Okay. So Arvato, you guys know what to do next? More food, yeah? Okay. But thank you for the pizzas, it was really nice. Okay, so a little bit of house rules. Chit chat, because this rule, just keep it to a minimal, just respect the presenters will be friendly, okay? If you guys want to eat, it's not allowed to eat over here, just go upstairs, that's where you take food or drinks or anything. Food waste, make sure you keep it to the minimal upstairs. If you eat anything, just make sure you guys take care of things. Alright? Our agenda is a little bit short for today, it will be really jam-packed and good. Alright, so first we'll be having a talk on serverless and Kubernetes. Right, I'm sure everyone is familiar, but we'll go a little bit into that. Second, we'll have a lightning talk as well as hiring from our Arvato system will be coming up to here as well. Third, our open source hardware. This will be a really interesting topic to those who are inside hardware related stuff. And lastly, it's our discount code. So make sure your cameras are ready. I'll make sure to announce, when to actually take out your phones, right? Take a picture. Alright, so without further ado, let's go to our first talk, serverless and Kubernetes with Fission by Fission.
Thanks for the brief introduction. So this session is about serverless and Kubernetes with Fission. Before getting into the session, quickly about me. As he said, so I'm Jyotimani, lead DevOps engineer. I lead a team of Kubernetes engineers, and I also write just blogging. You can find more at options.help, where I post day-to-day challenges we face in DevOps and tech. And I'm also one of the Cube astronaut, work of 4 Cube astronaut certified from people from Malaysia, right? So Fission. So before getting into this Fission, I'll start one of the traditional way to start a presentation. Like, how many of us use Kubernetes? Okay. Sorry, I couldn't come up with a better way to start a presentation, but yes. Yes. Fission, as most of us heard, so it is a serverless, lightweight framework which runs on top of Kubernetes, which helps to handle workloads and use cases better. Like, what kind of workloads and what kind of use cases? Let's get deeper into the presentation. And I also have a short demo where I can show you how Fission can be used in the real. So Fission lies in the serverless landscape of Kubernetes CNCF suite of tools. And so there are also other alternatives for serverless frameworks like OpenFast and Knative. So OpenFast, if I say, it's premium version, and Knative, it does serverless, but it does a lot of other things as well, right? It gives massive suite of tools. So Fission is made, it lies in the sweet spot where you can quickly experiment serverless on top of Kubernetes without very much distractions, right? So I have focused more into this presentation. It should quickly help you to onboard and trying out Fission easily in Kubernetes. Right. And quickly about, so Fission supports a lot of other languages like Python, Go, Node.js. They even support Perl, and it keeps growing as well. So I don't want to explain the more details about the architecture about the Fission, but let's understand the concepts of Fission and then have a quick hands-on so that you can quickly get in and try a use case in your production environment and your environment. Right. So Fission. So there are 3 core components which we should consider, and we should obviously get hands-on is function, environment, and trigger. Right? So function is where our business logic lies in. So function is something out of the Fission that executes your code. Let us say you have a business logic which executes a certain set of code whenever the action is performed. That is where the function lies in. So function can be anything that satisfies your need. Right? So environment, it depends on what kind of language which we need our function to be deployed in. So that's how environments are classified. It can be a Python environment, Go environment, or Node.js, whatnot, right? So environments, on the front-end side, it helps us to provision the baseline for the function. and it helps us to keep a warm pool of nodes. So whenever a trigger or a request is received, it immediately provisions and executes. Right? And the other part is the trigger. So trigger is whenever the trigger happens, it helps the function to start the reaction, right? So there are a lot of ways to trigger a Fission or a serverless function, like HTTP triggers, timer triggers. HTTP triggers, you will get a REST endpoint where you can call that, and that eventually trigger the function, right? And timers, as the name says, it's a cron job. You can also trigger cron-based activities and queue-based activities, and based on the metrics from queues. So you can also integrate with this data. And one of the interesting trigger which I like is the Kubernetes watch triggers. So one of the example of Kubernetes watch trigger is, let us say we can watch for a certain namespace and watch for any kind of event that is happening inside the namespace. It can be a pod creation, pod scaling, pod termination, or pod getting into unschedulable state. So based on the event, capture the event, and we can write a custom function that does some operations. Right. So queue watcher is whenever it is executed or triggered, it will keep on monitoring the Kubernetes events and Kubernetes API. Whenever, and based on the event, it will do the action. So here is an example which I would like to explain. Right. So Fission is a CLI. Fission comes with a CLI which helps us to communicate with the Fission installed in the cluster. Right. Fission, so I'm creating a cube watch type of trigger. So my watcher name is Arvato. I'm applying it in the default namespace. So I want to trigger my function named log event. So how to create a function and everything we'll discuss further later. But let us assume you have a function ready which does a logging activity and sets a logs somewhere to a third-party tool or Datadog, some Elasticsearch or OpenSearch, right? And type pod and filter added. So what this means is it watches for the default namespace whenever a pod is added or created. Only in that particular event, Fission function will be triggered, which in turn runs and executes and does your job. So this is one of the interesting use case. Cube watch. Yeah, you can also try it out. And the other part is executor, right? So executor is a virtual component which takes care of executing the commands whichever we give to the Fission, right? So executor has two major components. One is the pool manager and a new deployment. Pool manager helps us to keep the warm pool of nodes based on our environment preference. So if it is a Golang pool or as a Python pool, it will make sure warm pool of functions are ready, and once it receives a trigger, it will deploy. And new deployment is something newly introduced in Fission, right? So, compared to pool manager, it has a higher port star, but this is helpful for handling a large number of traffic compared with the pool manager type of use case, right? So pool manager is for lightweight, does a one-time job, and new deployment is for heavy use case. So using pool manager, we will get a port start time of 100 milliseconds. Right? That's one thing to note. And yeah, quickly into the demo. I'll show you the demo. So I already have the cluster installed, so I don't want to get embarrassed here. You don't want my installation to be failed, right? So installing Fission is quite simple and easy, right? I can show you the command. So it's a one-step install. Quickly have your Kubernetes cluster ready and put it in your terminal. Your Fission is up and running. And these are the quick handy commands. So I have installed my Fission components in the Fission namespace. So these are the core components of Fission. So apart from whatever we discussed in the backend, this is what happens when we install or when we execute something, right? So build manager, which helps us to build Is it okay? It does not support more than that. I'm sorry. Is it okay? Better than before? Okay. So, I was saying, build manager is a one which helps us to configure or package our deployment and be ready for executing the function. So, executor, as we discussed, it's a executor which helps us to execute a function, and these are the default triggers which comes up with Fission installation: queue voucher, database trigger, router, and storage is for saving this persistent storage, which creates a local file system link, and timer is for the cron job activity, right? And the book based triggers. So I already have an environment. The environment is where, which decides a type of code which I'm going to write. So I already have an environment for Go, which I prepared already, which is ready. And let me check whether I have any functions here. So I already have a function. I will also show you how to create a function from scratch as well. So to quickly test this function, so this is a plain hello world function which comes with this Fission. So let us create a new function. So I have a sample Go app here, which So I have a sample Go app which directly hits open source weather API and gives us a JSON response. It's not that complicated. So let's functionize my application. So this is a CLI which invokes a helps us to create my function. So I'm creating a function, naming it as demo.go, and the environment is Python, and source is weather app.go, which is located at the Fission demo directory, right? And entry point is handler. So handler is where the function will be called. So if you're familiar with Lambda functions or cloud runs, where the init handler or Lambda handler, where main function resides. So there's the same concept here. So we should encapsulate all our business logic into the handler, so that handler calls a subfunction and returns, right? So I have a handler function, so it's a single function app, directly calls open source API and returns. Okay, I have the demo created. Okay. So when I created a function with plain Go, weather app.go, so the build executor will take that as an input and compiles my Golang code. We can see the compilation output and everything here, and creates it my Go binary and keeps it ready in the warm pool of nodes, right? So if our compilation fails due to any a compilation error or syntax errors, we can see and capture from the build executor logs. So I have the function successfully ready. Let me show you the warm pool of nodes. So we have once I initialize the Go environment, executor will make sure I have the one pool of nodes for my Go app. So these are the one pool of nodes which is ready. And since I already installed my function, they are already interlinked. When I do trigger, like the Fission test is directly testing with the Fission CLI, which sends a dummy signal to execute the function. And as I said, there are a lot of ways to trigger the function. Okay? I'm going to trigger my demo function. Yeah. Right. So this is a function. I got the output. Simple weather app, which gives us a response immediately when I trigger the function. So this is one of the use case, and there are a lot of ways to expand based on our business needs. Fission can be really useful while handling lightweight automation tasks which we want to do. Right? It can be based on Kubernetes events with kubewatch or cron jobs or the webhook triggers, everything. Right? Yes, that's all I have for the demo. Any questions on the Fission?
Any questions?
Yes.
All right, then one over here.
Hello. Since we got like Keda can actually scale down to 0, and this does seem to have quite a lot of overhead. So have you done a comparison of this Fission versus just
Keda.
using a standard Keda where you can scale down your things to 0 and there's no traffic? So,
see, even with Fission, we have integrations with Keda. So Keda is for event-driven architecture. It does not create the one pool of nodes for you. You still have the cold start time of scheduling the pod, bringing the pod up, which eventually takes based on your application logic and Docker image size. Right from scheduling to get the pod into running state, there are a lot of stages, right? You need to schedule a pod, find a node, schedule it, put the Docker image, get it into running state. You can avoid those complexities with Fission. So if you have the business logic ready, which can be easily functionalized, you can deploy it here. So this is mainly for the use case where we use Lambda functions or Cloud Run in the cloud environments in AWS and GCP or not, right? So this is an alternate framework which runs on top of Kubernetes to use other than those managed cloud provider versions.
Hi, I'm Kwang from Talk. So my question is, how do you structure your repository or CI/CD for this? Because previously we wanted to implement something similar, but in the end we don't know how to do GitOps or whether we should have a separate repository for it. So my question is, how would you structure your repository and how will your CI/CD flow?
That's a good question. I just have a sample architecture, but haven't tried in production grade, but it's still in the R&D phase and going on. The recommendation would be categorize based on the business use cases. We can categorize our APIs. So obviously they are going to be tiny independent functions which does the job. So categorize based on that and create a CI/CD pipeline in the native environment. Right? So let's say you are in AWS or Google Cloud. Use a native tool like Code Pipeline, a cloud build, which directly integrates with a cluster and which establishes a connection with the cluster rather than executing directly from a GitHub or a third-party CI/CD run, which has a secure way of connecting to the cluster and does the Fission CLI to install and connect to the cluster and does the job. So that way we can. So Fission CLI is best way to automate whatever you are working for.
We have any other questions? Going once, going twice. Okay. Okay, all right. Thank you so much for the question. we have a special lightning round talk for today. Alright, so I'll give it up to Magesh. Alright, round of applause.
Just a very quick one. Not that special, but it's something called Cloud Native Heroes Challenge. So this is out fresh out of the QCon from North America, Salt Lake City. So they just announced last week, if I'm not mistaken. So anyone can join, as long as you are major. I think anyone here. So what the challenge is about is, so you need to be, so we have open source source codes available and people are attending that, right? So what we need to do is going against the patent trolls. So what are patent trolls? They are the business or any entity that take the patent from a company that already has patented something. So they look for the companies that are going defunct. So they try to buy the patent and try to create a lawsuit. So this is kind of backing for open source projects. So CNCF has announced this Cloud Native Heroes Challenge, where you maybe work on some lawsuits and try to find out the patent trolls and also try to find out the prior art. What is the prior art is you try to tell them that they've already implemented the solution even before it went into the patent. So that patent is no more valid. So these are the things that you need to study and study from the lawsuits and present that to CNCF so they can protect these open source projects. So from when you join this challenge, if your solution is accepted, you might win prize varying from $1,000 to $3,000 per lawsuit, per prior art that you submit. If you win, okay? And you also get to win some specs from CNCF. Just a quick one. So you can go check Cloud Native Heroes Challenge, what is it about, and contribute to open source. That's it.
So just to add on over here, if you guys maybe are not familiar, big companies, you know, don't want to name them, but I'm sure you already know, maybe it's your phone or something. Alright, so what they do sometimes, alright, not only big companies, but what they do is that because they have so many resources, they go around saying that, hey, I did something this before, for example, like a folding phone before. But in the real world, they didn't. So what they do is that they go to court because they have lots of money. So they go to court and say, hey, I did this before. So you smaller company can't do that. So I'm going to lawsuit you. So that's where they actually do if they can't buy companies. Right? Alright, let's move on. I think you guys are actually, if you don't know, quite familiar with Dr. Sean Tan. He's actually dubbed the Doctor of Chipsets, right? The Doctor of Chipsets, yeah. He started off as engineering student, but he also does law. Is that correct, Dr. Sean? You also did law, right?
I studied law.
Yeah, studied law. So I saw his LinkedIn a little bit, alright? Okay. Other than that, he also did his PhD in Cambridge, UK. So he's very, very well versed in what he does. Alright? So any kind of technical questions, you know who to go to. Alright, back to you, Dr. Sean.
Sekejap lah.
Okay, bagi masa sikit Okay. Alright, over to you.
Alright, testing. Oh, cool. Alright, good evening, everyone. Welcome. Thanks for coming. Let me just see what the time is. Agak time. Alright, cool. Alright, so the title of my talk is Open Source Hardware. Alright, so I was invited to come and give this talk. And I was thinking to myself, alright, I have a room full of people who are like, system administrators, SRE, alright. What am I going to talk about? Then they say, talk anything about open source lah. So I'm like, okay, open source, then what to talk about? Okay lah, I do open source hardware. Okay, because I'm very sure you're all very familiar with open source software. I'm sure you use it in your daily, right? It powers your daily life, right? So that's something that a lot of people are very familiar with, but maybe open source hardware might be a little bit more niche. Okay, so I thought, okay lah, just do a quick intro to open source hardware, right? So I'll talk maybe about 15 minutes, and then after that I'll open the floor to questions lah, alright? So before we begin, quick intro to myself. Just now, the host already gave a bit of an intro. This one a bit more intro, got picture one lah, okay? This one got, you see, got, this thing is called newspaper. In case people too young to know what it is, alright? So this newspaper, as you can see, some of it quite old. This one is like 1997. Okay, so just now on the lift up, somebody asked me, how long have you been in the industry? So I had to answer since very long ago. You see hair all white already. Okay, since quite a while ago. So this was back in 1997. Where I first came out with my first commercial software product. So you all know how to do maths, so how long already, right? Now of course I started programming a lot earlier than that. I started programming in the 80s, okay, 1980s until now. Today I am still writing code. Okay, alright, like mainly C++ and Rust. Okay, but that one can talk like separately. Okay. What the host just now mentioned, I also happen to have a law degree. Law degree they want to do for fun one. Okay, they want to do for fun one. Seriously, I have no intention to become a lawyer. I have no interest in becoming a lawyer. Becoming a lawyer is shit work. Terrible. Okay, not worth it. Okay, better become engineer. Right? So back to our topic now. Our topic today is what is basically an intro to open source hardware. What is it? Right. So in general, right, the idea is fairly straightforward. Open source hardware is the concept of applying all the free open source software principles. The principles, right, but applied to quote unquote hardware. What do we mean when we say hardware? Right, so these are basically the things that we need, right? So i.e. mechanical drawings, schematics, electronic schematics, bills of materials, PCB layout, HDL source code, as well as IC layout. So that's a general idea. Okay, so we are applying the principles, not necessarily the exact licenses. Okay, but general principles. Okay. So what are all these different things? Okay, I'm sure there's something in this picture that you guys have all heard about. Maybe something you guys have used, you all have used before also, right? There's this thing at the corner there, the corner there, the little Arduino, alright? I think that's very famous. Right, so most of you probably heard of it or maybe used it before. Okay. So quite often when people talk about open source hardware, the first thing that pops into the head will be
Raspberry Pi.
Raspberry Pi. Okay, good. There's a slide on Raspberry Pi later. Alright, there's a slide on Raspberry Pi later. Alright, so but yeah, that's the kind of thing that pops into people's head. Arduino, Raspberry Pi, things like that. So I took the example of Arduino, right, just to show you. So in the case of the Arduino, what is actually open source in the Arduino? What? Right? Besides the software of course is open source. Right, but that one I don't talk about because that one is open source software, not open source hardware. Right? So on the hardware side, what is actually open source? Okay. So number one, you can definitely go and get the schematics. Okay, so this is actually the full schematic for the Arduino Uno. Right, the basic entry level Arduino board. Okay, the basic one. The Arduino Uno revision 3, this is the full schematic. As you can see, not very difficult, not very complex. Okay, very simple. That's why Arduino cheap because it's simple. Alright? So how does this apply in terms of principles of open source software is because you have the schematic, right? You can easily build and modify or change and then come up with your own little Arduino. Which is something a lot of people have done in the past. Right? They take the basic Arduino design, they may tweak it slightly, add some extra peripherals or add some extra features, right? And then they can still use the Arduino so-called software and ecosystem and everything to program their hardware. But their hardware can be modified or custom thing. It doesn't have to be exactly the Arduino. And it also allows, of course, the creation of all your cheap Chinese clones. Right? You buy the original Arduino, $35. You get one from China, 10 ringgit. Okay, so all you guys know lah. Alright, so it allows the creation of the cheap Chinese clones. Just get this and use lah. Right. So besides the schematic, what else is open source from Arduino? They also open source PCB layout. Okay, so this is the actual physical board, right? And also indirectly, they also provide you mechanical dimensions. Because when you do PCB layout, it also involves sizing. So there's also physical dimensions in terms of like these are the holes, these are the way you're going to put in the screw. Right? This is where you will have the header, USB header and things like that. Okay, so indirectly also got mechanical sizing in case you want to build like a housing or a casing for the Arduino. Right? So there's also information in there. So and people do that. They come up with all kinds of products. Internally it's a Arduino, they don't let you know. Internally it's Arduino, but outside they cover it with their own casing and they put their own logo and they pretend like some very super junky thing. Right? But it says Arduino. Right? So that's it. Now, is this good enough?
Definitely not.
Oh, why?
This is just a controller. We want a full-size computer.
Meaning what?
Like Raspberry Pi, you can run the server on it. This one you can.
Okay. That one's a separate issue. Right, that's a separate issue. That one, I said I got to start Raspberry Pi later. Okay. But is this good enough in terms of open source? Are you happy if you got this?
Oh, we need suppliers.
You need some what?
Suppliers.
Suppliers to what? Buy the product.
Yeah, buy the chip factory.
Okay. You need to buy chip. Anyone else? Okay, all the software Arduino give you you can download from them and use it. So anything else? Documentation also you can go online plenty lah. Anything else? Open source code in terms of? Okay, Arduino is a very good example, got a lot lah. Alright, a lot of students just use this for their projects, right? So a lot. Anything else is missing? The microcontroller itself lah. If you look at the Arduino, it doesn't just stop at the board. There are also chips. Right? There are also chips, and those chips on the Arduino, unfortunately, are closed. Right? They are closed. So Arduino goes down to the level of, alright, we got the schematic, we got the board layout, PCB layout, but the chips themselves, you go and buy lah. Right? Buy from, in this case, Apple, or now known as Microchip lah. The company is Microchip now. But you go and buy from them. Right, this one, important or not?
The most important.
It is the most important. Without that, there's no Arduino. Alright? So if one of the principles of open source software is this idea that, you are, in a way, you have the independence because no one can kill the project, right? Because once you got the source code, even if the original supplier die, right, you've got the source code. In other words, you can actually still survive, right? And we've got source code for all sorts of things all the way down, typically until here. Right? Until here, your chip is stopped. Okay? So for vast majority of people, this is good enough. Right? Because they can go and buy the chip literally can go and buy. Okay, no problem. But for people like me, this is not where it ends. Right? So I always like to joke when I say I do full stack development, right? Full stack for me means until
chip level.
Silicon. Everyone that's chip level. Chip also got many levels. Alright, down to silicon. Alright, so for me until this level not good enough. Alright, I want to know more. Alright, so that's where open source hardware also principle continues. It goes deeper as well. You can also find HDL designs. Okay, this is an example. This is just a slide of example. This is not a real one. Example of what we do when we want to do so-called chip design. Alright, this is an example of a language called Verilog. So when we want to do chip design nowadays, in the past, people used to draw circuits. Right? But nowadays, people don't do that anymore. It's not humanly possible to draw circuit for a chip with a billion transistors. Okay? I think the last major CPU that was hand-drawn was the Motorola 68K. That was a 32-bit CPU, came out in the 1980s, and that one was still hand-drawn. Right? Hand-drawn, but that one is called the 68K because it has 68,000 transistors in it. Okay, but that's about it. Now it's billions really, how to hand-draw. Okay? So what we do now is we use other tools. So we have languages, what we call HDL languages. HDL stands for Hardware Design Language. Okay? The idea of the HDL, if you look at it, it looks like code, right? But it's not to replace code. It doesn't work like software. The idea of HDL is to replace schematics. So in other words, this is actually describing a schematic. Okay, so the language actually describes the schematic, and then we pump it through some tools, and then out comes the circuit. Okay? The tools, we call them synthesis tools, but you can think of them like compiler. Put in source code, come out something, right? So same thing. You put in your Verilog code into the synthesis tool, out comes the circuit. Yes, question.
What are the examples of the thing you feed in? Like which port connect to which port, so on and so forth, or what?
No. Okay, that's a good question. And since we got time, I sidetrack a bit. Alright, HDL describes the circuit. How do we describe the circuit? Alright, so we start with the inputs and outputs. Alright, so usually we declare some module somewhere, and then you have a bunch of input and outputs to describe these are the wires. These are the wiring. And then after that, we have some extra code. This code describes behavior, i.e., the behavior given this input to some processing, right? And then you get some output, right? So it describes behavior, and that's typically the kind of Verilog code you find. A Verilog or VHDL, the two main popular languages, VHDL and Verilog. It will be behavioral. So you're actually describing behavior, right? So, and if your background is electronics, you sort of know what I'm talking about, in the sense that in electronics we have certain basic building blocks. We have things like flip-flops, we have things like multiplexers, we have things like logic gates and things like that. So instead of describing every single logic gate manually, that one is not feasible. A billion transistors is probably like a few hundred millions of logic gates. Okay? So not feasible to describe every logic gate. But I can, for example, put in behavior of the code that says that this is an adder. I do A equals B plus C. So when I do A equals B plus C, the synthesis tool, when it parses it, you'll know that, A equals B plus C, so you want an adder. So the synthesis tool will put in the circuit for an adder. Alright, and then you want to, the output there, you may connect it to something, let's say a flip-flop. Right, you want to connect to a flip-flop, you write the code for a flip-flop, the output, then A equals B plus C, and then the A goes somewhere. The A goes somewhere, then you have to write the code for a flip-flop. There are many kinds of flip-flops in this world. You write the code for it, and then the synthesis tool will look at it and go, okay, you want this particular kind of flip-flop. Then I wire it up, adder, wire it to a flip-flop, and then so on and so forth. Alright, and then once, so you write the behavior of the code, or rather the behavior that you want to achieve, and then the synthesis tool spits out the circuit. Okay, so a few interesting things about this is, number one, this is a common mistake that people make, especially people coming from software side. You look at it, it looks like code, then you start thinking in terms of code. Alright? The problem is thinking in terms of code, you're thinking linearly, right? Step by step. Circuits don't work linearly. Alright? Circuit is completely, massively parallel, quote unquote, / concurrent. Right? When a wire hits a branch, it doesn't go either left or right. It goes, the electric current go where? Both direction, left, right. If got 3 branches, it goes all 3. Got 5 branches, it goes all 5. Alright, and then you just keep going and going and going. So therefore, that's why I'm saying a very common mistake that people make when coming from software, it looks like software. Looks like code. And you start thinking in terms of step by step, then you die. Right? It's not that way. That's why I say, this is, you have to think in terms of hardware, and then you write the code that describes it, describes the behavior that you want. Right? And then there's two will just speed it up, speed up the circuit. Okay? So that is this level, HDL level. And then after you process a few more things, then you have to go and make a chip, right? Right? You have to go and make a chip, you have to send to the fab like TSMC or in Malaysia we got Silvera. Okay, how many of you know Malaysia got fab? Got one hand. 2 hand, 3 hand, okay. Good enough, better than 0. Right? Okay, so we do have a fab in Kuala Lumpur. Okay,
How many nanometers?
Don't talk nanometer, talk micrometer. Okay, okay. Well, they can do like 0.13, 0.18. So it's about 130, 180 nanometers kind of thing. Old technology, but okay, still can use, right? Okay, don't be so concerned about the size, right? Right. So you want to send the thing to a chip fab, right? What you do? You need to give them something that looks like that. Okay, so that's the last bit that I mentioned just now, the IC layout. So layout, if you look at that, that's literally how it looks like when we visualize it. Okay, a chip. If you actually take a microscope, you look into the chip, it looks like a massive construction site, right? With plenty of buildings and highways connecting them. Right. So because basically that's what chips are. We build them by layers. So there's a basic substrate, which typically is silicon, right? Silicon. Then after that, we've got layers. So we've got oxide layer for insulator. Then we add the gate, right? Then we add the connects. Then we add layers and layers of wiring. So that's why you see like a few lines, straight, long lines at the top. Those are metal wires that fly around, connecting everything together. Okay, and the bottom is where you will find things like the transistors and all that. Those are the structures at the bottom. Okay, so we have to come up with something like that, this kind of information, and then we pass it to the fab, and then they will build it layer by layer. Just like a construction site. You build a condo from the foundation, you build it up floor by floor. Alright, so similarly with a chip, you start with the foundation, the silicon, and you build it up layer by layer until you get a chip. Okay, that's not a question over there.
Just a quick confirmation. This is what is called silicon wafer, is it?
This is not the wafer. This is the design of the structures that will go on the wafer. Okay, so the wafer is the base, right? The silicon, the wafer silicon is the base. That's the substrate material. Then on top of that, we will start adding all kinds of things, and those things are usually not silicon. That's why you read the news that some of these things use very rare metals. Right? I don't know what kind of metals they have used nowadays, but all kinds of rare metals. And the wiring, we will typically nowadays use copper or aluminium because it's cheap. But the olden days chips, if you guys can find some old chips, right, it's all gold. So you can get the chip and melt it down. And nowadays, 1 ounce is 200. How much? It's like almost 300 ringgit already. Right? Per gram or something like that. You melt it down. Okay, it's gold. It's literally all the wiring at the top are these long highways, right? Like highway one. Those are the metal layers. Okay? That's all gold. Okay, so and that's the lowest layer. With this layer, you send to the fab, they will be able to make any chip for you. Okay, alright. So for me, if you want to be open source, it has to be open source all the way down to here. Alright. Yes. Correct, you're right. So if you guys if you all have ever done PCB layout before, then in concept it's very similar, You put your circuit, you do your wiring, and the manufacturer will tell you what the tolerance that they have. Like your wires, how thick can they be, right? What's the spacing between wires and things like that. So similarly, if we do low-level chip design like this, similar kind of thing. The fab will give you a set of design rules, what they are capable of doing. So that's where you hear the news that tell you, oh, we're going after 3 nanometer lah, 2 nanometer lah, 1 nanometer lah, whatever lah. All this, to me is nonsense when you get one. Alright? Seriously, when you get one. It just sounds sexy, good for investment, but practically not much difference. Alright, so so they will tell you all the tolerance and then you follow. And they tell you how many layers they can do, what layers they can have, what kind of materials they can use, everything else, then you follow. I know, that one is design rules. So that comes from the fab. So the HDL is usually vendor neutral. So just now you see the very loud code. This one is usually vendor neutral. This is just code, right? Which you can pump into all kinds of tools, for example, to do simulation, if you want to test it and things like that, right? This one is vendor specific. In other words, you have to pick a fab. So if you pick TSMC, you design your chip for TSMC's whatever 3 nanometer process or whatever, that can only be used by TSMC 3 nanometer process. If you try to bring it to Silterra will tell you, sorry bro, we cannot do 3 nanometer. Alright, cannot, not possible. Then you have to change your chip. The Verilog code can be the same, but this one will be different. And this one will be for Silterra instead. Okay. Alright, yes.
So, what is the thing that in the news they say that US don't let China use to design chips?
Okay, that political issue.
Which component are they locking down?
Okay, US is preventing the sale of what they call very, very high-end UV machines. Okay, ASML ultraviolet machines. Why? Why is this ultraviolet? Because how is this thing used to make the chip? This file that you send to the fab, they will peel it off layer by layer, and then they make a mask. You know what's mask? Imagine it's like one piece of paper, you cut out the hole, and you cut out the holes according to the drawing. Okay? And then how they print it on the chip, how they print it on the silicon, they put the silicon at the bottom, they pour some chemical on it, okay? Then they put a mask on top, and then they shine the light. They shine, in this case, UV. Alright? They shine the UV light on the chemicals. The chemicals will react to the UV light. Okay? So the parts that are exposed will react differently from the parts that are covered. Alright? So when they react, they will harden. Okay, harden. And then later, they pour some more chemical to wash it off. So then, parts of it will be exposed. Parts of it will be covered. And then after that, they go and pour the copper, the silicon, whatever, they pour. And then the parts that are exposed will then they don't pour silicon, they pour aluminium, copper, whatever, and those parts will then have aluminium and copper. And after that, they wash off the rest. Okay, so that's how the process goes. Okay. Oh yes, very messy, very, very expensive mess. Okay, as you guys may have heard in the news, what to set up a fab. Okay, to set up a fab costs billions. It's not millions, it's billions. Okay, then your question on the production, how much to produce? It all depends on how many lines of production you have. One line is like $1 billion, so how many lines you have? Number one. Number two, how fast they go from stage to stage. Right, like I mentioned to you just now, you take the silicon, and you put one layer, and a layer, and a layer. Right, so how many layers you have? 13 layers, 15 layers, whatever. And it's a lot of the work is automated, which is good. In the old days it was more manual, nowadays it's much more automated. Right? But it's still quite a bit of manual labor as well. That's why you see the chip plants, they will hire humans. Right? It's not just all machine. There are also humans in there walking around. Those wear bunny suit. Those people. Okay, cool. Right, so then this is the last layer. Okay, so continue on. Just like in, yes, question.
Question also use law exploration. So how is it when we finish with and use is it use law
All right, our friend here asked a question about Moore's law. Right, I'm sure you guys have heard of this word Moore's law and how does it? Okay, how does the nano thickness of the what you call the size, the node size, how is it related to Moore's law, basically. Okay. All right. What's the first question I'm going to answer is what is this thing called node size? All right, that size. What size are we talking about? Any ideas? Transistor size node. It's not talking about size of transistor.
Maybe back in the day, we used to refer to transistors, but now more or less refers to the point at which they want to achieve the density of the transistors.
Okay, what do you mean by that? No. Alright, I give you a simple answer. Simple answer. The simple layman understanding, very simple one. It refers not to the size of the transistor, but the size of the gate of the transistor. Okay, the gate. What is the gate? The transistor, as you know, is a switch, right? On and off. Okay, the thing that controls the onness or the offness is the gate. Alright, so the gate, you have a transistor. Okay, no whiteboard, never mind. Whiteboard. But no, never mind. Okay. You imagine, I'm standing here. This is the silicon. Alright, this part I got something called the source. This part I got something called the drain. These parts are conductive. So got wire, got current. But this part is not. This part is what you call opposite of conduction? Insulator. Okay, so this part is insulator. Alright, so this part normally no current. Alright, then I construct something called a gate. I put it across here, and then I connect it to a wire, and then the wire I can send a signal. Right? The signal can be on or off. Right? So let's say I send a positive current, what's going to happen here? Because it's positive, right? It's going to attract electrons up, and when enough electrons are attracted up, it forms a conduction channel across. Then the current can flow. Alright, so that's why it is related to the size of the gate has an impact on the performance of a transistor. It has a huge impact in many different ways, which most people don't care, right? But it has an impact, right? So the idea behind this Moore's law, Gordon Moore, he made this observation long time ago that this Intel is one of the guys who founded Intel, right? So in Intel they noticed that, okay, what did they notice?
Transistor size double the speed.
Double the speed. Anyone else?
Every
Double the transistors. Anyone else? Double efficiency. Oh, very good. Anyone else? Okay, you're all right. Okay, why I say this? I just want to point out that Moore's law doesn't actually mean anything. It's a marketing thing. Over the years, it has been defined and redefined in so many ways to ensure that Intel is always number one. Okay? No. Intel not yet died, right? They are what we call 100-pound gorilla, 100-ton gorilla. Not so fast die. Yeah, but they got a lot of cash reserves. Oh, then they will got money the point that got money Intel haven't died yet. In case you all got Intel stock not doing very well, but Intel haven't died yet. Okay, not yet. Right, so the point I wanted to bring up was Moore's law has been redefined so many times that it's basically become very meaningless. Okay, alright? But the general idea is that something will improve regularly. Okay, it could be density, i.e. the size of the transistors will shrink. It could be speed, right? But you also notice CPU speeds went up. Pentium 4 we got 3.8 gigahertz, and then after that, what happened? 1.6 gigahertz. Alright, so like I said, when they hit that and go down, they redefine Moore's law. Alright, no longer about clock speed. Now it's about something else. Alright, and then they move, and then they redefine it again. Okay, so that's the thing. Alright, but how it has an impact there, how it's affected there, let's say it does have an impact, because if let's say we look at clock speed, generally smaller gate, faster. Because the amount of time it takes for the electron to flow from here to here, faster. Shorter gate means faster, right? So you can switch the circuits faster. Right, but smaller transistor also mean more leakage. Your current will leak. Okay? So also not so good. So that's why a lot of it has impact, but whether what kind of impact, positive, negative, different stuff. Yeah, that's one question.
So what's theoretical question, but what happens when the gap of the transistor gate comes down to 1 electron? How do we do it to know beyond that?
Okay, got a good question. The question is what happens when the gate of a transistor, the size comes down to the size of 1 electron cannot alright, 1 atom Okay, if 1 electron is smaller than an atom already, then susah already. Okay, I don't know. Okay, but that's a good question. What if it comes down to the size of 1 atom, 1 silicon atom? Okay, 1 silicon atom. Honestly, that day is not that far away. If you look at what's happening today, the sizes are like a handful of atoms now. Alright, it's like not that much now. It's like you're not talking about 100 atoms anymore. It's going to be quite small. Alright, so we are nearing that day, which is why a lot of people are always nowadays there's a lot of research into finding alternate materials. Silicon is good because it's bloody cheap. Where's silicon from? Sand, alright, because shitloads of it in the Middle East, right? Plenty, alright, go pick up the sand, and you can make silicon, alright? So it's dirt cheap, literally dirt, right? But we're nearing the limits, so there are a lot of research going on into finding other more novel alternate materials. Okay, good. Yes. Okay, our friend here got asked a question. Just now I mentioned there's leakage. So what happens when there's leakage Alright. Okay, the short answer is means your battery life will be lower that's the short answer Theoretical transistor is supposed to only use current. That means it's only supposed to use current when it is switching. That means when it is off, alright, it's not supposed to use current. Sorry, not transistor, a gate, a logic gate. When it is either a 1 or a 0, it's not supposed to use any current. It's only supposed to use current when it switches between 1 and 0. Alright, that's just the way it's designed. That's just the way we designed it. So, that is true in theory, but in practice is current is always leaking all the time. Because electricity is on. Right, so once the electricity on, even though this is what we call an insulator, what's the meaning of insulator? It just means it's not a very good conductor. It doesn't mean that it doesn't conduct. There's probably a little bit of current flow, but so little that it doesn't impact. Right, so there's always a current, so less battery.
Does the leak have anything to do with, because there's a lot of jargon in the media, something like quantum tunneling and stuff, is it related?
No, it's not. Quantum tunneling is a completely different concept. nothing to do with electronics, electrical current. It's got to do with the phenomena of pushing electrons through an insulator. Okay, so we can do that. We have the ability to do that. If you have an insulator, alright, that you want to be able to pump electrons through an insulator, it is possible. Alright, and this technology today is mainly used in something that we use every day, flash memory. How does flash memory work? Flash memory is very simple, not difficult. You got a gate, and then you get another gate. So then you got 2 layers of gate. The middle layer is not connected to anything. It's something that's called floating gate. But because it's in between the actual gate and the transistor down there, it affects the formation of this channel. So if you can charge that floating gate, i.e. you pump in a lot of electron, it will become easier to turn on. You take out the electrons, it will become harder to turn on. Alright, so then you can store data. It's not dangerous, it just okay, that one is the same for all storage. If the medium corrupt or decay, then it's gone. Alright, let me continue. Alright, okay, I got a few more. I promise you a few more. Okay, a few more. Alright, so this is a bit of law. Right, just to tell you that in Malaysia, it's a bit interesting. We have some unique laws that help to protect this open source hardware. Alright, there's Patent Act. Unfortunately, in Malaysia, patents don't really apply to, in this case, not directly. Okay, so and it doesn't apply in software either. In case you guys don't know, Malaysia we don't recognize software patents.
So we can pirate Microsoft Office lah.
No, that's not patent. That's copyright law. Okay, different. So Copyright Act, next one talking about is Copyright Act. Alright, copyright we recognize. Okay, so in the case of open source hardware, Copyright Act applies on a lot of things. For example, your schematic, you can copyright it. Okay, because it's considered a drawing. It's treated the same as like artwork. Okay, it's a drawing. Your PCB layout, also artwork, can copyright. Okay, if you do Verilog, that's considered literary work, like Shakespeare. Okay, so that one also can copyright. Alright, so Copyright Act will be able to protect open source hardware if you guys are working on it in Malaysia. Okay, Trademark Act, trademark we know it's all branding Alright, so if you got branding, then of course Industrial Design Act largely applies to if you got mechanical drawing. Right, because you may be designing the housing for the device, not the actual electronics, right? The housing can also be protected. Okay, either under industrial design or a design patent. Either way, also can. Right? Industrial design is easier. No need to show functionality. Right? No need to show usefulness either. Yeah, patent must show the patent must be something special, novel, useful. Alright. Last one. This one is this is why generic. This is unique. It's like a handful of countries in the world we have this. The last one. Layout designs of integrated circuit act. So that one protects, just now I mentioned to you, the mask. Right, the lowest level. That one, in Malaysia we have the law to protect that. Most countries, 90% of countries don't. Any ideas why? Most countries, 90% of countries in the world do not have that protection. In the layout design.
They don't have the capability to produce?
Correct they don't have that. Exactly. No fab, no ability to produce, got protect for what? Okay, no one in the country is going to work on this anyway. Okay, Malaysia got, I said we got? No, Silterra. Okay, that one Malaysian one. Okay, so we have Silterra. So government want to protect Silterra. Right? Malaysia boleh. Malaysia boleh. Right. Okay, so that is the loss. Now, last bit, I promise you got the slide on Raspberry Pi. So my question, one simple question to you guys is, what do you think of the Raspberry Pi? Does it fall under open source hardware? That's why I put question mark there because you see, you ask people, when you ask people what is open source hardware, one of the things that pop into the head is Raspberry Pi. But then you think about it a little bit harder, how much of the Raspberry Pi is actually open?
Just the circuit. Just the circuit.
Just the software. Even the software, not the whole software. It's not the full stack. You don't have access to the GPU firmware. And in case you didn't know, the GPU is the one that controls the ARM processor. In the Raspberry Pi, when you first turn it on, the ARM processor is sleeping one. The GPU comes on, it sets all the necessary configuration flags for the ARM, then it turns on the ARM.
Why?
That's why you can put in like in the text file, right, in the SD card there, you can turn on, turn off whatever features. That's why a config of text file. Who's reading that config of text file? Not the ARM. You can even set clock speed there. The GPU reads it.
Why this design?
That's the way they design it lah. You ask them lah. Okay. Right. So the firmware for GPU not available to you. So that the GPU firmware is kind of like your BIOS or your UEFI thing, the first thing that boots up. Alright. So you don't have access to it. Right. So software also not the full stack. Right. Hardware wise.
.com.
Got lah. You go to the website, you can find the schematic. Alright? But the schematic not complete. Alright? So yes. Okay, our friend here got a question of how does RISC-V or RISC-V fit into the question of open source hardware. In case you guys are not aware, there is a new CPU in town. Okay, not that new lah, more than 10 years already. Alright, but it's recently becoming sexy lah. RISC-V. What is this RISC-V? People say open source hardware. I'm like, what is RISC-V actually? It's not the design.
Instruction set.
Okay, yeah, exactly. I say RISC-V is a piece of paper. It's documentation. Alright, you go to the RISC-V website and download, they give you the specification. The specification is literally chapters, alright, of what this CPU is supposed to be able to do. Okay, what about the design of the actual CPU? Nothing. That was up to you lah, how you want to implement. Okay, so therefore, you can go online, you can find all kinds of implementations of RISC-V from all kinds of people, including yours truly. Okay, you go to my GitHub, you can find. Alright, I also got do one lah, it's fun lah, this like about 8 years ago lah, do for fun lah, okay? Just to implement a RISC-V, okay? So when someone tells you that they buy a RISC-V CPU, for example, it's not like ARM, ARM, the CPU all come from ARM. Alright, RISC-V CPU doesn't come from RISC-V. It comes from some other company that decided to implement the specifications. Right? In other words, different company will have a different interpretation of the specifications. So the CPU is going to work differently. Okay? Yes.
Then what if you compile something by it will not be the same?
Yeah, exactly. So our friend here question is, if you compile code for one RISC-V, can it work for a different RISC-V? The short answer is, it depends on what kind of software you're talking about, number one. Right? Because it may be instruction set compatible, but there are a lot of features that it may not be compatible. Okay, so chances of it being like, let's say, we are spoiled by this whole Intel idea that you can just write a code for one CPU and just run it everywhere. The only reason that happens because Intel bothers to maintain like compatibility and things like that, right? But RISC-V, one manufacturer to another manufacturer, I wouldn't bet on it. I wouldn't count it. Probably cannot. It's more likely cannot than can. Because they're supposed to implement their own specification, they're not supposed to copy each other. Right? So it will not be exactly.
Then what is the hoo-ha so-called progress they are talking about?
Oh, RISC-V. RISC-V now hoo-ha because of China. Why? Because you know US now not friend with China, right? Politics again, right? So US not only restricted, let's say ASML, right, the selling of the UV chips, but that's with regards to manufacturing. And with regards to design, they also block Intel, block ARM from selling the newest designs. Okay, so because China has got certain joint ventures, because certain JV with ARM and also with like AMD, right? So they can actually produce the latest lah, right? But with this new politics thing, they say no. Okay, so what happened now? China say they have to be independent. They cannot rely on Intel and ARM. So maximum funding for RISC-V. So that, and you can see a lot coming out from China. A lot of little RISC-V CPUs coming out from China, or from all kinds of different companies. Okay. So that's how it plays in. Okay, so RISC-V is sexy now. Okay, so if you're interested in doing like chip design, interested in CPU, now it's RISC-V lah. Anything else? Oh yes.
Then how does this fund in a knowledge, how does this fund compare with Intel?
Oh, you mean performance-wise lah?
Anything related?
Okay, his question is how is RISC-V in comparison to, let's say, Intel? Okay, RISC-V in comparison to Intel, if you ask me, does this company do RISC-V, there's a company called Intel, which one I put my money in?
Intel.
RISC-V. Unfortunately, I've been telling investors this for more than 10 years already. Intel is dead already. Alright, it's been dying for a long time. It's a slow and long death. It will continue to last a slow and long death for many more years to come. Alright, but it is on the way, it's out now. Okay. And the problem is not technical. Any other questions? Yes.
I have two questions.
Not
to RISC-V.
Okay.
The first one is, can you explain a little bit on chipset yield? Because for example, yield. So for example, you have Vivo chipsets, which is quote-unquote better, non-Vivo effect. That's number one. Number two is, since you are CEO and co-founder of your own company, how does geopolitics between what is happening in Taiwan and France comes in implementing or giving positive impact to Malaysia?
Alright. Okay, so you got two questions. Let me get you correct. First question is about yield. Yield. What is this yield and how does it factor? Alright. Second question is geopolitics. China, Taiwan fight. How does it affect me? Alright. I answer second question first. Easier one. Alright. China, Taiwan fight. Go to war. How does it affect me? In terms of business, no big deal lah. Right? Because I don't really have any dealings with either country lah. Not much lah. Alright. So doesn't really impact me much. A small company, right? I'm not Intel, right? Small company, right? No big deal. Personally, got a bit more impact lah. More impact because my wife from Taiwan. Okay, that personal one. Okay. Alright, second question Alright, first question is yield. How does that impact things? So first, what is yield? Alright, yield is this jargon, basically very easy to understand. In terms of chip design, it's just if you make one silicon, right? You got one piece of wafer so big, you make a lot of little chips. Let's say you printed 100 chips. Out of those 100 chips, how many boleh pakai? That's the deal That's the meaning of yield. How many are spoiled? So if you make 100 and then let's say 20 are spoiled, then your yield is 80% lah. Okay, so how does it impact you as a consumer? Two ways. Number one, if the yield is low, it means more expensive, correct? Because given one piece of silicon, the cost is fixed, You buy that one piece is fixed. You print that whole piece, right? You print the whole bloody piece, 100 things inside there, and then only 80 can use. The other 20 you makan right? So you have to feed. Basically, the loss there is back to the consumer. Right, first thing. Second thing, how it impacts you, the company will cheat. How they cheat? These 20 that are so-called not working, correct, meaning they'll go and test a little bit, try a little bit. Let's see if I reduce the clock speed a bit, suddenly it's not working already. Okay, I got 10 more. I got 10 more, so now my yield 90%. But the other last 10 must run at lower clock speed, cannot run at higher clock speed. So what I do, I sell them.
New range, new product.
It's new, but it's the SE version lah. This is your Pro, the Pro. And this one is your SE version lah. Or sometimes they take the 10, the last 10 the last 10 that's still broken, right? You take the last 10, you go and cut a bit. Cut, because the chip got many different parts, right? Many different parts. Let's say they printed the chip of 4 cores, or 4 CPU, then they cut off 2, the 2 broken one. Left 2 still can use one, Then what happened?
Cotodo.
They come up with another product line, that is even cheaper, but half the horsepower. Then that's how they improve yield. Because chip yield is actually very bad. You can think about it, you are trying to print something with the size of nanometers. Anything happen, there was a small little Richter 5 earthquake in Taiwan. Slight vibration. How? Gone already. Because you are shining one light, a beam of light onto something with the size of a few nanometers. One little vibration, gone already. Your vibration don't even need to be much. It's a few nanometers vibration, boom, gone already. Okay? Don't say earthquake lah. The guy kicked the machine, right? Gone already. Okay? So and then all kinds of things like dust lah also can impact. Why? Because the size of dust is huge compared to the size of the chip, right? So all kinds of things can affect yield. So yield is actually pretty shitty most of the time. Okay, you'll be lucky if you can get 70%. Very good already. Who benefits and supports open chip hardware design? Same kind of story as who benefits and supports open source software. Okay, so in terms of for example RISC-V, some big companies will so-called, they join the foundation, they pump in money, they will put in resources in order to keep this alive. Why? Because it's very good competition for ARM. Right? Because I can tell you in ARM, their biggest existential threat is not Intel, is RISC-V. Okay? So you keep RISC-V alive to keep ARM on their toes, so they are not monopoly, they have to charge a bit cheaper. Right?
Okay, so we'll take one last question.
Okay, last question. Maybe last two?
Okay, last two, yeah.
Last two.
You say you pick RISC over Intel, right? Do you think that CIS architecture already hits its limit, already enough potential? That's why you pick RISC architecture.
Okay, good question. Our friend here asked about CIS architecture, whether or not its lifetime is over. Alright, it's been over a long time ago in the sense that all CPUs today are no longer CIS or RISC. They are all the same. Even though Intel started off as CIS, in terms of its architecture-wise, over the years it has transitioned. Today now it's actually entirely RISC backend with only the CIS compatibility front end. Okay. So when CIS instruction goes into an Intel architecture, Intel CPU, first thing it does, it converts the CIS instruction into what we call micro-ops. Those are RISC instructions. So you imagine it's like you have a kind of VM just-in-time kind of thing running in the background. Okay?
So nothing is pure CIS or RISC?
Nothing is pure CIS or RISC anymore. Everything is hybrid. Yes, last one.
How does the M1 Ultra Fusion chip connect together? It literally put two chips together. How does that work?
Okay, so that's another very good question. Your question is more on the packaging rather than the design of the chip. So I mentioned just how you design the chip. Once you design the chip, you need to wire it up to the board. Normally, we wire up to the board. So that's packaging. So in the case of like the M1, one of the smart things that Apple did was they put the CPU and then they put the RAM, the memory, right next to it, and they wire it up directly. So it doesn't go through the PCB, it doesn't go through the board. It's on the same physical chip. But those two things, right, the CPU and the RAM, they are built separately. Because the process for building RAM is different from the process for building CPU. Okay, so even though it comes out of TSMC, they both come out from TSMC, for example, but it's different process, different steps. So by wiring it up directly, what happened? The wire is only like 1 millimeter, 2 millimeter away. So the electron only need to flow 1-2 millimeter. So therefore, very, very fast. Super fast. So that's one of the tricks that they use to give the M1 additional boost. Compared to your Intel, right? Your DDR RAM is on the motherboard. So your Intel processor has to go to the motherboard, travel through probably, I don't know, 2 cm, 3 cm of wire. So it's 30 times slower. Oh, you mean internally lah? Okay. Okay, I don't know specifically, but normally how this would be done would be they would have placed them next to each other on the silicon and then the ones that can all work together, they sell as ultra . The one of you spot one they cut and then they sell as the non-ultra . Like that . Okay. Okay, thank you very much.
Okay, thank you.
Actually, still got 6 slides but never mind.
I think everyone was very much interested. Yeah. Okay, please do.
Oh yeah, last one this is my LinkedIn . So if you all got LinkedIn, you can scan the QR.
Okay. Alright guys, so the next agenda for today, I'll be sharing some coupon codes. So make sure your phones are all ready to take pictures. Okay? We'll give it a few more seconds to scan. 3, 2, 1. Okay, I'll proceed to So I hope everyone found Fishon's properly interesting. I think Dr. Sean will be flooded with questions at least once you go. So Dr. Sean is okay with that. Alright, so carrying out with the agenda. Okay, so are you guys ready with your phones to take the codes, coupon codes? Okay. I'll move in 3, 2, 1, yeah? Alright, 3, 2, 1. Great, take the pictures. So this is the code for today, this is Cloud Native KL. So make sure you guys take a picture of the code and do it straight. You guys can. Just for your information, these exams are worth $300 to $400. So 30% off is really a lot. Okay, so make sure you guys do. Alright, I'll wait 3 seconds for this. Okay, all good. 3, 2, 1. Okay. Alright, so we are looking out, for sponsors, for if your company is willing to give us, a menu and stuff. Okay, we're also looking for speakers too as well. So please do scan the QR code. Alright, and we're at the end of today's month. So thank you so much everyone for your time today.